Thank you. It's a pleasure to be here. And the first slide up here, when Leslie invited me here, she said, "Oh, we're going to meet at Gates Hall, and the lecture is going to be at Gates Hall." Immediately, this picture popped into my mind. I'm an architect. This is Gates Hall at Cornell University, the brand new building. And the second slide is, I'm an architect. I graduated from Cornell in architecture, and the college, at Cornell, there's a full college of architecture, art, and planning. And architects, we work with engineers all the time. In fact, we love engineers because you guys do a huge amount of work for us. And we get to design buildings and work with engineers. And so I'm used to going to Cornell. I was very used to interacting with engineers. And when I went there, one of the main topics, yes, Earth Day and all of that was starting, but one of the main topics was computerized graphics. And one of my early experiences was the formative computerized graphics were jointly developed or partially jointly developed at Cornell and in the architecture school and in the engineering school. And it's a collaborative event, and that's when I really learned the value of engineers. So now we're going to go to a slightly different view of climate change. How many of you taken an art history class? Anybody? Oh, yes. Yes. Good. If you take an art history class, you look at things in a different lens, and that's what I'm going to try and go through in these next few slides. This is a slide of the Mediterranean. These are three ancient ruin sites: Leptis Magna, Ephesus, and Kurion. Has anybody been to any of these sites? Anybody seen pictures of any of these sites? Okay, good. The issue is that the Mediterranean, in climate sense, has radically changed in the last 2,000 years. There's lots of reasons why, but we don't really know, there's no definitive answers as to why things change. So I'll start off with the first site, which is Kurion. This is a little Google map, and up on the left there is an ancient sanctuary site to a god of Apollo. And in this case, it's a deity of Apollo called Apollo Hylotes, which is Apollo of the woodlands. So he's a nature deity of Apollo. It's basically the worship of, nature, fundamentally. Apollo is a god of strength and represents strength in a lot of things. But in this case, in Cyprus, he's a nature deity. There's a city site to Kurion down on the right. I haven't shown that, but just there's an exercise, Roman ruin there that you could play sports in or whatever, just to give you a little sense of scale. So this is the temple of Apollo Hylotes. I did the restoration work on this temple. When I started work on it, the foundation was about this high when I came to the site. And over the course of about 4 years, I excavated stones, I laid them out on the ground, and I interpreted what the temple was. And after I left, actually all the stones were laid out right on the ground, right here next to the temple. And then a number of years after I left, they took all the stones and put them back up vertically. The columns are new because we didn't have any column shafts in it, but most of the other stones are antique stones, and the whole upper segment of the temple are the main stones that I joined and put together. None of that was known until I did this work. So here's the sanctuary site. The temple's at the top, and you can see how it's self-contained within a forest, and there's nothing outside of that sanctuary. It was really for roaming deer, it was for animals, and that's how they really looked at the world. So what this is really saying is that in ancient culture, their value system was correct. By the art, by how they worshipped, by what they built, we knew that their value system was correct in order to have a successful society. The one other little aspect is there's a little circle up there in the sanctuary in the upper left, medium upper left-hand area. When you find Apollo, you start looking for Daphne. And anybody read their Daphne, their classics in terms of, okay, Apollo chases Daphne. When Apollo touches Daphne, she turns into an olive tree. So what you do is you start to look for Daphne. Oh, there was this unnaturally flat area to the site. And I said to the archaeologists, we should just dig over here. And we found Daphne's garden. We found evidence of tree pits where trees would have been planted in a little circular walkway. So we actually mythology actually fits the site. And the Greeks were great on this. It was like a recipe. Okay, next site is Ephesus. This is on the coast of Turkey. This is the Ionian coast of Turkey. Ephesus was like New York City of the ancient world. It was commerce, commerce, commerce. And then all of a sudden, Ephesus disappeared from being an important city. And what happened to Ephesus? The site's way over here, where it says EFES. And then there's that little marsh right now in the modern Google map. Well, that was their port. And that used to be connected to the ocean. So either the sea fell, the land rose, or some sort of combination of siltation happened. There's multiple events going on here, and you have the death of a city. And this is equivalent, in the ancient world, this is equivalent to New York City. This is not a small thing. So things went wrong. We're not totally sure. A lot of people go for the whole siltation thing. I think the answer is more complex. But it really can show you the amount of change that can happen to geography within 2,000 years. So Ephesus is a little map of the ancient site. This is a great site to go to. This is the ancient library in Ephesus. And at that time period, this would have been essentially the Stanford University of the ancient world. That's all the knowledge of the world this was one of the centers of the knowledge of the world at that point in time. Now, this is also the theater at Ephesus. And you really don't even see the whole thing. It keeps going up the hillside. Theaters are great because you can start to scale the size of the city that you should anticipate based on the size of the theater. It's like scaling the size of Stanford from your football stadium. You know there's a big university here, otherwise you wouldn't have a stadium that big. So we use theaters as a telling sign of how big the culture was, what they were really doing. This is a phenomenal theater. You should go see it. Sometime in your life, you should go to Ephesus and see this. Okay, the third site, this is a Google image of Leptis. This is on the coast of Libya. And I was really hoping things would go differently in Libya so we could all go to visit Leptis. The beaches are great. This is the Mediterranean coast at its best. But up in the middle of that picture, there's another silted-in harbor. The ancient harbor is that whole green area up there. And it's a similar story. We see large changes in Mediterranean cities, and we really don't have all the answers. There's a theater see that way up on the left? There's a theater. And then way down on the right, there's a Colosseum. And both are large. So we also know Leptis was a big city. Here's the theater. Not as big as Ephesus, but here's the stadium. And by the way, all of our stadiums are based off of Roman stadiums. They have been for forever. This would have been a very lush climate 2,000 years ago. All trees. This is a very different visual than what was there 2,000 years ago. Okay, now I'm going to shift to another point in time. And this is the year 1100 in the borders country between England and Scotland. That red dot up there, if you get in the big map up there, that little red dot's the borders country. There was a lot of trade at that time between Belgium and this area and the borders country in Scotland. And the 4 red dots on this little Google map here are abbeys. Abbeys were the equivalent of like a small New England college. So you could get on your bicycle and ride between these 4 small New England colleges. The question is, why, how, why in the year 1100 there's this level of sophistication and 4 colleges sitting in a place where you'd never even think anything was going on. This is 200 years. You guys watch Braveheart, the movie? You know, they're like, you know, he's living in a mud hut. But this is actually 200 years before Braveheart and the battles. And those Braveheart battles were within 10 miles of these dots. So the question, we see a rise in civilization in this very specific way. And you have to start to figure out, well, what happens? What are all the key things? Is it the climate? Is it the people? Is it the wars? How does all of this interact? Well, this is one of the abbeys. This is Melrose Abbey. There's a little plan of it up there. That's the remaining part. This is the nave here, and this is the main part that is built. Well, you know, those Braveheart guys were a lot more advanced than what was shown in the film, is the bottom line. And this is a very important center of culture at that point in time. This is Jedburgh Abbey. This is one of the other ones. This rivals in size what you would find in Paris in the 1500s. In terms of, or in Florence, if you go to Florence or Paris and you see larger cathedrals, they're largely based on these earlier versions out of England. And the abbeys were also French. They were Benedictine and a whole bunch of different names. Cistercians were there. They were all allied with France. It's sort of like you had a college out here, but there was a main university down in France or something. They were all talking to each other and trading. So what is this? I mean, this is like Jack's teaching art history here. And so if you haven't ever taken art history at this point, I'm going to say, you can go to a class and you can spend all semester looking at slides of architectural history or art history, and you should do it. Because this is just a little intro, and it'll give you a very good perspective to look at our modern problems. Because basically you're seeing the remains of failed societies, and then you can start to contemplate what the problems really are. So what does this have to do with climate change? Okay, this is a reconstructed temperature graph. I have no clue if it's accurate or not. But if we're way back here in ancient times, you can see the theoretical temperatures stayed pretty level. Right here at the year 1100, boom, the abbeys were built. What happened? It warmed up in southern Scotland. So agriculturally, that area took off. What happened around 1200, this is when Braveheart, it's starting to go downhill a little bit. But by 1600, those abbeys are ruins. They were ruins in about 1500, and they're gone. Little ice age coming. The whole economy collapsed in this part of Scotland, and it never recovered. Now, there were a lot of wars and things like that. There were a lot of contributing issues. But the question is, it's a direct evidence of the effect of climate change and the importance of dealing with climate change in a reasonable way. And then we have the graph here, we're just heating up again. So now I'm gonna switch over to my company. As an architect, I've created a little company on how to build buildings. The fundamental principle is, can we drive buildings down? Right now, I'd say electricity use, buildings use like 47% of all electrical energy. can we drive the use of that energy down so low that all the other technologies, every advanced technology you could think of, because you simply have to use less of an advanced technology or an expensive technology, is that a better solution to buildings? And it's the issue of waste. How do we get waste out of the system? We can always come up with systems that solve the problem of waste, but can we solve the problem of waste on the root level? And that's where my company is headed. We have a structural technology and a thermal technology. So these 4 little blocks up there are the structural technology. And it's a model idea of interlocking blocks. You can see those blocks. You have male corners, female corners. Everything interacts on every axis. And if we consider the space between the blocks to be a wall, you get a structural form of those 4 blocks. And I actually made the 4 blocks, and then I put this really loose caulking in between, which is just like putty in your hands. But as soon as you do that, you can take a soft material, put it in there, and you can twist it, and it all interlocks and is extremely strong. So this is what's referred to as a composite structural solution. And you're thinking, well, what are we trying to do with this? Well, what we're trying to do is those blocks we want to be the size of this room. Then we can be inside of them. Then what we want to do is we want to take those blocks, we want to stack them up, we want to make really tall buildings. And then we want to pour the concrete last. Well, what have we done? We've created a reinforced concrete building with a cellular structure that has no rebar. All the cost in building buildings, every building on campus here is just loaded with rebar. It's hand labor, it's everything. We're trying to automate the process of building. We're trying to build buildings in a different way. So I've got a little video. What would a presentation be without a video? So we stack boxes. Oh, we even get music here. Then we pour the concrete in as glue. And then you have a building. And I just picked a historical building for this. But that's how we want to fundamentally change building from a construction process to a manufactured process. We want to change the structural characteristics of the building and how we build buildings. And we can do all this. This isn't an issue of not being able to do it. If we think in new ways, we can actually do these things. So the other technology we have is we end up with a wall system that looks like this, with a little curvy wall. If I showed you this picture first, you say, well, no one's going to build a little curvy wall. It would be like way too much labor. But when you invert the build to big boxes, and then you get the curvy wall, it's really easy. In fact, it's easier to build a little curvy wall. Now, straight walls are kind of lazy, but any curved form is always taut, is strong. It's like ready for stress. And that's really what the structural aspect here is. The other technology we have is a thermal technology. And if you look at this, maybe the next, I'll go in, well, the thermal technology is that how do we create walls that have a better insulation value? For driving energy use way down, how do we do it? Everybody says, oh, just more insulation. Well, it's technically the wrong answer. When the astronauts went to the moon, they didn't carry a lot of insulation with them. You didn't see them like, big, doughboys out there. They actually had very thin layers of insulation. And at that point, NASA developed ideas on insulation about radiant and convective and conductive energy and dealing with all of them. And that's why the astronauts survived up there. We're essentially doing the same thing. The building industry is slow. I'm here 30 years later saying the building industry needs to adopt a technology that NASA adopted and promptly forgot. And then we're reimagining it for buildings. So what's the advantage here to this little curvy wall? You get all these little airspace voids. If we do the right things with these air spaces, we get a super insulation. The performance of this 8-inch wall is over R60. Anybody familiar with R values? It's a measure of heat transfer through building materials. The only problem is R values are fantasy. It's like visiting the fiction section of the library. They're technically wrong. They were invented by the fiberglass industry to make fiberglass look good. And it just ignored radiant energy totally. So the fundamental solution is to, I'll go to the next slide, is to create little foil layers, a little blown in, it could be urethane insulation, anything, and to have little air spaces with foils on both sides of a wall, and you get this superior thermal performance, R60 and above if you equivocated it to a bad scale, and it works. We've actually put it in a number of houses as test beds. This is a foil on the outside. It's a special foil. This is like a nano-deposited foil. But when you reject radiant energy early, you have a really good chance of having extremely energy-efficient buildings. So we're bringing both of these technologies to market. There's a third technology, sort of a little derivative technology that we developed. And we took our box technology and we're currently marketing to the DoD because they have a little containerized buildings all over the world. When we wrap these buildings, we wrap the floor with a super insulation. Well, the number of buildings with a super insulated floor is approximately 0. It's very, very rare. They do it in the Arctic, but it's a different thing. They just lift the building way up. But what we realized is if we did a super insulated floor system, put it down on the ground, the ground source geothermal energy down 6 feet, which is what geothermal heat pumps run off of, comes to the building. It migrates right to the building in about 30 days. So the DoD had never even thought, in fact, you can read in their things, don't use ground source geothermal heat pumps in the desert, or don't use them anywhere in the world because you have to dig trenches down 6 feet. And we just sort of raised our hand and said, no, you don't. If you create a building that is so energy efficient, and the thermal box that we're proposing is 7 times more efficient than what they have out there, and you put a source that's 4 times more efficient on creating heat, which is what a geothermal heat pump is, the resultant building is a 28x improvement over what the DoD has in place overseas. Then every piece of solar, every piece of anything you want to do becomes affordable as a technology. Everybody's worried about new technologies and how to make them affordable. What I'm saying here is drive the demand into the floor first. Then every idea you guys come up with is an economically viable thing to deploy on buildings. Oh, this is a little 28x. What is 28x performance? So if we did it on a gallon of gas, and the old buildings, you see old clue, if you ran just the efficient part of the building for an hour, the heating system, you'd be able to, a gallon of gas, and you'd keep that building heated or cooled for 4.4 hours. The brand new clue containerized building that the DoD has, you get 8.8 hours. And then our containerized building, you get 275 hours. Yes?
Making the building more efficient drives down the cost. It drives down the cost of making, like, eating it up or whatever,
Yeah.
Things like that. But that would also, not just help sort of, renewable energy, but also, fossil fuel consumption too. So that doesn't necessarily, that would necessarily, be an advantage, because if you could even, heat your building with coal, like at a cheaper price than solar cells or solar thermal. So how would that incentivize someone going for renewable as opposed to going for fossil fuel sources?
Well, on the economic basis, driving demand down is the least costly. There are many studies on this. Driving demand down is always the least costly option. And I'm just saying do that first. So if you put everything back into cost per kilowatt hour, you'll see that energy reduction is the best payback to be spent. And energy production is the most expensive thing. But we have to do both. We have to make green energy, we just have to consume it, better. So let's see, we have a little picture. These are some of the building designs for the DoD. Yes?
2 questions. One is, depending on the size of the kind of building blocks, how do you transport them? Say it's like in a city, how would you actually transport one of those building blocks?
Yeah.
To build a house or something of that nature. And then the second question is related to building stock and how quickly it turns over and what the penetration rate of this type of building might be.
I'll answer the second question first. Over the next 25 years, we will build 1/3 of our building stock new. We've gone through a time recently where rehabbing old buildings has been the central focus, and I will contend that will continue, but the new building is about to begin in a very large way. We will build a lot. The opportunities are really going to be on new buildings. And your other question was the
transportation.
The transportation.
Yeah.
There are guidelines on transportation. It's not pretty. The bigger the box, the more you pay is the issue. You can get them there. The maximum box size might be about 12 by 12 by 64 feet. Fortunately, we can cut out all the sides. You can stack them up, you can cut out sides, you can join them up so that you get bigger spaces. But from a market point of view, we're targeting condominiums, and those are highly cellular building topologies. Question?
That's what I was going to ask.
Okay.
If you can take the walls out.
Yeah. You can pretty much fully cut out all sorts of things. In other words, if you took one of those boxes and cut out half of it, it would still be very, very stiff. It's a structurally efficient form.
And would they be manufactured in like a factory or something like that? Okay.
Yeah. This is like, just like Tesla has a factory over there, we want a factory like that. And we just want to make big boxes and ship them and build tall buildings, Yes?
What would be like the first building that you'd like to see implemented? Like, would it be a hospital? Would it be an office building? Would it be a retail outlet? Like, what would be the first? Like, what is this most ideal for right now? For the low-hanging fruit.
The first, we think the DoD is going to be first because they have a very ugly, they're running these bases off of diesel generators. So the equation for them is really ugly. We gave them a life cycle study, a 25-year building life cycle study. Capital and operating expense for our base versus their base were half the cost. Total cost were half of what our government is currently spending. And so we think that's a compelling case for them to go first, but the DoD sort of have a time frame all of their own. We have no clue when they're going to say yes, but they're interested. On the commercial side, we feel that housing, probably senior housing or affordable housing, or housing for the homeless are all going to be viable contenders for early adoption. It depends on how much pain the governments are feeling. Then the governments will say, let's build some net zero housing. And our current marketing is that on the commercial basis, our buildings will be 10% less to build, and they'll operate at about a 40% cost savings versus existing. And so developers are really interested in this. But we do need governments to say, we want net zero. and we want grid-free. We want resilient buildings. We need the governments to say this, and the developers will just follow. But the governments have to say that first. So I'm throwing up a little business model slide because we can have all, architects, we're great at ideas. We think of ideas all the time. It's a matter of bringing those ideas out into the real world. So we have a business model here that our business is we virtually create our buildings, and then that virtual reality of the building eventually moves into a factory, and that factory then produces the containers, and they get transported, and we build two things. We build tall urban net zero housing for the commercial market, and we build net zero containerized living units for the DoD. We've identified 3 states as being the growth areas in the country. It's California, Texas, and Florida. And we're looking to get the product out there and start. Yes.
What about like the building codes and like how can you comply through some other alternative to compliance or materials like?
Yes. We are building code compliant, not in our most sophisticated form, however. In the most basic forms, we can build under the codes today. But as an illustration, I started to talk about R values. When I first designed the thermal system, the R value calculated out at R12, which is non-compliant. You have to be about R22 to be compliant. We eventually figured out how to get it to calc out at about R26. And there's some tables in the ASHRAE handbook that nobody's looked at for decades that allowed us to make that interpretation legally. And that's part of the code. So we actually can fill out the forms and comply. But we're actually building an R50 value performance level. And the California Energy Commission actually recognizes that this is a technical problem, because what it does is it devalues our superior technology. It's not recognized for its performance level. And that comes when you build buildings and people aren't going to buy. You say, oh, it's going to be less to operate, and they'll just say, no, you can't use that figure. And then once you devalue a technology, it's harder to get it adopted. Well, the California Energy Commission actually put out a building envelope grant application, which we've applied for. We applied for it ourselves, Lawrence Livermore National Laboratory, and Arup Engineers out of San Francisco, to study the physics of heat transfer in buildings and get away from the R value system. And so we're prepared to, we also went in with the Navy. They gave us a site down near Death Valley, which is really, really hot. They have an air station down there called China Lake. We found the most extreme temperature location in California, and so we want to do a little demonstration and build some buildings, model them, do the physics work, and then hand that back over to the Energy Commission. And yeah, there's a lot of, yeah.
What type of foundations do you have to build to support these buildings, and also how long does it take to construct them, since they're already modularized?
On the commercial, we put a standard foundation under the urban housing buildings, the 30-story buildings. The idea for earthquake is called base isolation, where the structure is highly cellular and rigid, but the whole building has a little shift at the bottom. And but besides, everything from that point down is pretty standard. It would be standard port concrete. We're interested in everything moving up. In fact, we'd probably be up one level. A lot of urban buildings want a big open space in that first level, or the first 2 levels. Then we go into the smaller pieces up above.
And how long would it take for construction?
Yes. We think our buildings are about a 30% savings in time in a city. And that's also a big deal for governments. If they value that, there's street disturbance issues, all of that. We also know that we can do net zero buildings in an urban environment. And the first phase of that is to use combined heat and power in the mix of a building. And once you introduce, are you guys familiar with CHP? Once you introduce CHP, you could have a PV building that's hyper efficient with CHP in the basement. Pretty much you just have to bring a gas line into the building. You don't need to bring an electrical line to that building because the CHP can take care of your electrical loads.
So how would it be net zero in that case?
You know, I'll let the CHP make they're right on the edge of net zero or non-net zero. If legally, I think that industry has decided, they've convinced everybody that they are net zero. But I'm not going to really defend that. I'm just going to say that's the early adoption stage. They'll be replaced by more efficient PV. They'll be replaced by flywheel power or something. All of these technologies are in play, and we're just going to utilize whatever the most enabling technology first. So I'm just going to finish off on the temple and. Did anybody ever, I put out that you should go read Vincent Scully's book. If you don't take an art history course, you should read this book, The Earth, the Temple, and the Gods. It's a good read. It'll give you a really good perspective on cultures and why we value the environment. What's the point of saving everything if we can't figure out what we really value? And we need to build the cities that we can live in, that our culture can thrive in, and that we can value. And that's what the ancients, did. And they did it really, really well is the issue. The architecture right there that they invented is a dominant form of architecture everywhere. You can see it all over your campus. Little porticos, it's the Greeks. That's where it all came from. So, any more questions or?
Do you have more questions for Jack or from the reading about sustainable design, some other examples that we had? I have a question. You raised the issue of these disappearing cities, their harbors had changed, went away. Mm-hmm. It looked like it could be possible to have just changed their location of where they were shipping from and changed where their building was. What was going on? You've roamed around there. You must know. When you likened it to New York City, this is very relevant.
Mm-hmm. Ephesus did change. They created a new port city 10 miles away called Kusadasi, and that city is still there. That's still a big, thriving city.
Okay.
So Ephesus was such a radical problem that they actually created a new city. Leptis, North Africa didn't fare well. And so I think the climate change in North Africa was so radical. You have a whole series of cities the size of Leptis. And you can go to places in North Africa with huge theaters in the middle of nowhere, and you say, oh my, there must have been a big city here, and you don't see any evidence of it all. So I think North Africa just baked. It lost its topsoil, it lost its rain, and it just baked, and it never came back.
So here we sit in California with a horrific drought going on.
Yeah.
I mean, you're seeing that as part of what's been changing. Yep.
Yeah.
Does your building, this was something I was thinking you might have in mind, make things more resilient to climate change, and how? Certainly being net zero is wonderful. You're not making the problem worse with more emissions, but
Yeah.
are your buildings more likely to withstand changes,
Yes.
and how?
We're working with Lawrence Livermore Laboratory, and
Okay.
they're the only place in the world that can model buildings for destructive testing on their supercomputers. And they have written software that just sits on their computers. It doesn't exist anywhere else. And you can make buildings implode. You can launch projectiles at them.
Oh,
You
boy.
could put them in the worst storm you would ever want. You can do anything. You can put any force onto them, and they will analyze them at the atomic level of destruction. And they're very interested in moving the technology, that analysis technology, out to market. They love our buildings because we're a composite system. And so there's a lot of redundancy built into cellular systems. They likened us to a beehive, that if you push on the outsides, the center stays good.
Yes.
And so they want to, do a lot of analysis for us.
Exciting. Is this provoking any further questions, thoughts? Some of you were worried about smart grid. Do you have? I mean, you're.
I have a opinion of the smart grid. I think islanding independent buildings as a microgrid that have their own resiliency is the smartest thing to do. There are too many factors. I mean, that Metcalf station was shot up a year and a half ago, just south of San Jose. And have you guys read about that? Yeah. Okay, it's a substation that was shot at just with a bunch of guns. And the substation almost went down. If it did go down, there would have been a blackout in the entire Bay Area. It didn't quite go down. And that's not resiliency at all. It's just exposure. And we have to reimagine how we're doing things so that the buildings themselves have resiliency. And autonomous function and independence is a key issue. I have no problem with the grid being there and everything, but it's not the only solution. If you make that grid really, really smart, it still has exposure on a physical level. And what I'm saying is, let's create, and the technologies are very easy for things to be islanded. Stanford has its own little power system right here. I'm sure they could, if Metcalf went down, Stanford would just be humming right along. They just disconnect from the outside grid. And so those are very important technologies to have.
Going back to the durability of the building, you talked about withstanding physical and climate conditions. How about chemical conditions, like maybe accident and things like that? Because as emissions increases and things like that, how would that affect the chemical integrity of the buildings?
Yeah, let me answer that in a broader. One of the things I advocate is, I've showed you ancient civilizations that radically changed when carbon wasn't moving around. Everybody's blaming carbon. They're like saying, oh, carbon's going up, the world's gonna, whatever. It's not the only reason, is what I want to say. I think there are 100 reasons why temperatures are going up, and we don't even think about all of them. And I fully believe carbon's a big picture thing here, but I think there's a lot of other things going on that we don't know about. And we have to broaden our minds to say we shouldn't be creating a society that is taking unnecessary risks in unknown ways, because it's going to come back to haunt us. We'll solve the carbon thing, and then the temperature still goes up. We don't know that. It could. So maybe we have to solve the carbon thing and 3 other things in order to.
I'll agree that there
Yeah.
are amplifiers, like the melting ice then further exacerbates things. So yeah, it's certainly true.
And I just want to. These societies all perished, and carbon wasn't a factor. Well, they were cooking over fires. Who knows what they were inhaling? I'm not sure, but,
Right.
probably just shortened their
Change
lifespan or
happens.
something. It's a different effect of carbon. They just, something like that.
Yeah, thank you. Any other questions for our speaker? let's thank you very much.
Okay, well, thanks.
Wonderful.